In this demo, we perform real-time analysis when running on a number of convolutional neural networks deployed on 3 off-the-shelf platforms targeted for embedded applications. The platforms include the Intel Edison containing a dual-core x86 CPU, the NVIDIA Jetson TX1 containing a quad-core ARM A57 and X1 embedded GPU, and the Zynq FPGA containing both a dual-core ARM A9 and a Xilinx 7 series FPGA that has our custom SparkNet accelerator running. For the Zynq containing the custom accelerator, we also exploit sparse-based reduction techniques applied to the networks. In the demo, we target 2 computer vision image classification tasks, targeting the smaller Safar10 dataset and the more challenging ImageNet dataset. For the Safar, we utilize VGG-style CNNs, and for ImageNet, we utilize AlexNet and SqueezeNet CNNs. In terms of performance, we measure 3 key metrics, including throughput, power utilization, and energy efficiency, which are plotted along the bottom in real time. We first target the Safar10 dataset. We begin by running on the Intel Edison CPU. Once the network is loaded, we begin seeing on the top the actual images being classified, and the far right we see the actual labels that are being assigned along with their probabilities. We see that for the Intel Edison we are able to achieve a throughput of 3 images per second with power requirements of 2.5 watts. This provides an efficiency of 1.2 images per second per watt. The throughput is quite low and not well suited for real-time applications. We next target the same network using the Jetson TX1 GPU platform. This is able to achieve a significantly higher throughput of around 100 images per second, but around 12 watts, giving an overall efficiency of around 8 images per second per watt. This is roughly 6 times improvement over the CPU. We next run on the Zynq FPGA containing the SparkNet accelerator. By exploiting the accelerator, we are able to achieve roughly 62 images per second at only 2.5 watts, providing an efficiency of over 25 images per second per watt. This gives approximately 20x improvement over the CPU and 3 times improvement over the GPU. Similar results are seen for the bigger VGGD network. Now we will switch to the more difficult ImageNet dataset. We again begin with the Intel Edison CPU. For the network, we first start with SqueezeNet, which requires 50 times less parameters than AlexNet, but with similar accuracy. For these bigger networks, it takes a longer period of time to fully load the network and to begin performing classification. Once fully loaded, we see that the Intel Edison CPU is able to achieve a very low throughput of 0.25 images per second, or rather 4 seconds for a single classification, at 1.8 watts. This gives a low overall energy efficiency of 0.11 images per second per watt. We next switch to the Zynq FPGA with the SparkNet accelerator. By exploiting the CPU and FPGA SoC with the SparkNet accelerator, we are able to achieve a throughput of 11 images per second at 2.6 watts, giving an overall efficiency of 4 images per second per watt. Finally, we switch to the Jetson TX1 with embedded GPU. Once loaded, we see that the GPU is able to achieve a very high throughput of 37 images per second at around 12 watts, giving an efficiency of 2.8 images per second per watt. The FPGA and GPU are able to achieve sufficient throughput for real-time applications. The FPGA, however, is able to target at a much lower power and is able to improve efficiency by 36x over the CPU and by 43% over the embedded GPU. Lastly, we repeat with AlexNet. We omit the Intel CPU because the classification delay is too long. The Jetson TX1 with GPU is able to achieve a throughput of roughly 25 images per second at 12 watts, giving an overall efficiency of 1.8 images per second per watt. Lastly, we run on the Zynq FPGA. The Zynq FPGA with SparkNet Accelerator is able to achieve a throughput of 11 images per second at 2.8 watts, giving an overall efficiency of 3.9 images per second per watt. The FPGA is able to achieve 2 times improvement over the GPU in terms of energy efficiency. Overall, we see that by leveraging the FPGA with SparkNet Accelerator, we are able to achieve efficient acceleration that is able to provide real-time throughput at a much lower power requirement. In particular, the Zynq FPGA is able to achieve up to 20 times improvement over pure CPU implementation on Edison and 3 times improvement over GPU-based acceleration on the Jetson TX1.